Eon's from CMU. His advisor is Hui Zhang. He's going to talk to us today mainly about some quality of service work he's done in the internet, but you may be familiar with some of his other work on scheduling algorithms and multicast. Over to you, Eon.
Thank you. Okay, so let me start. So as you can see, the title of my talk is a stateless core architecture to provide scalable services in the internet. Let me first start by stating briefly the problem I'm trying to solve and the main contribution of my work. So one of the fundamental problems in today's internet is that it has limited resources and management capabilities. As a result, the current internet is prone to congestion, denial of service attack, and cannot provide any meaningful delay and bandwidth guarantees. To address these issues over the past decade, two classes of solutions have been proposed: stateless and stateful. Unfortunately, none of these solutions is good enough. In particular, while stateless solutions are highly scalable and robust, they can only partially address these issues. In contrast, while stateful solutions can fully address these issues, they are much less scalable and robust than the stateless solutions. The main contribution of my work is to provide the first solution to achieve the best of the two worlds. That is, to provide network services which are as powerful and as flexible as the ones implemented by the stateful solutions, while maintaining the scalability and the robustness of the stateless solutions. Next, I am going into more details to present and justify the problem I am trying to solve. Then I am going to present and discuss the limitation of the existing solutions. After that, I am going to present our solution, which consists of a network architecture called Scalable Core, or SCORE, and a technique which is called Dynamic Packet State, or DPS. I am going then to demonstrate the applicability of this solution in one particular case, providing guaranteed services. I am going to end up with conclusions and future work. So, as you probably know, the internet is a packet switching network. This means that the information is broken into packets, and the packets are queued and forwarded by routers. In case of congestion, that is when the arrival rate at a link is greater than the link capacity, the packets are delayed, or if the buffer overflows, they are dropped. During this talk, I am going to use the term of flow to denote any unidirectional stream of packets between any two endpoints in the internet. These endpoints can have multiple granularities. They can be processes, they can be hosts, or at the highest granularity, they can be subnetworks. As you may know, today's internet still provides one basic service, and this is the best effort datagram delivery. Such a minimalist service allows routers to be what we call stateless. That is, accepting the routing state, which is highly aggregated, routers do not maintain any fine-grained state about the traffic. This allows the current internet architecture to have two highly desirable properties: scalability and robustness. However, as the internet evolves into a global information infrastructure, there is an increased need to provide much better services, such as quality of service and network support for congestion control. With quality of service, on one hand, we want to be able to provide delay and bandwidth guarantees to support new applications, such as IP telephony and video conferencing. On the other hand, we want to provide service differentiation in the sense that, for example, if one user pays twice as much as another user, the first user will get twice as much as bandwidth. Now, congestion control refers to all the mechanisms which are implemented by the end host and by the network to deal with the congestion in the network. And arguably, one of the best-known congestion control protocols is the one used by the TCP. The problem here is that the current internet is built around the TCP congestion control protocol. This means that it's very hard to deploy new congestion control protocols which are not compatible with today's TCP, but are appropriate and are required by new video and audio applications. A related problem is to protect the well-behaved flows such as TCP against the ill-behaved ones. To illustrate this last point, consider the following very simple example, in which you have one UDP flow which doesn't implement any form of congestion, just blasts the packets at 10 megabits per second. And 31 TCP flows, we share a 10 megabits per second link. So here, I'm showing the average throughput over 10 seconds for each of the flow. The UDP flow is represented by red. It's also the flow indexed one here. Here I'm assuming, these are, by the way, simulation results obtained by using NS2 simulator. Here I'm assuming a router architecture in which the packets are simply served on a first-in, first-out basis. And also, when the buffer overflows, only when the buffer overflows, the packets are dropped. And this is still the dominant router architecture in the today's internet. So as you can see, such a router architecture is very ineffective in containing the aggressive UDP flow and protecting the TCP flows. So basically, the UDP flows get more or less the entire bandwidth, while the TCP flows do not get anything. And this is because, if you are looking at this link, congested link, as long as there are packet losses, only the TCP will react. So the TCP, what happens in this case, then when it loses a packet, it will interpret that it's a congestion in the network. And as a result, it will slow down its sending rate. And because the other guy, the UDP flow, sends always at 10 megabits per second, as long as the TCP flow sends some packets, it will be always congestion. And the TCP will repeatedly lose packets, will repeatedly slow down until basically it doesn't get anything. So the bottom line here is that today's router architecture is not appropriate for providing this kind of protection between the more aggressive flows and the well-behaved flows. Next, I'm going to spend some time to present the existing solution to provide these better services, existing solution to try to address this kind of problems. Starting with the late 80s, two classes of solutions have been proposed to provide quality of service and network support for congestion control. And these solutions are usually classified in stateful and stateless. The main difference between the stateful and stateful solutions is that while the stateful solution requires every router to manage and maintain per flow state, stateless solutions do not require routers to maintain any fine-grained state about the traffic. As a result, the stateless solutions maintain the current internet advantages in terms of scalability and robustness, but on the downside, they can provide only weak services. On the other hand, stateful solutions can provide powerful services. Several examples are they can provide guaranteed services and also achieve high resource utilization simultaneously. They can also provide fine-grained service differentiation and fine-grained protection. However, they are much less scalable and robust than the stateless solutions. To illustrate the difference between the service which can be achieved by a stateful and a stateless solution, consider again the previous example. So here I'm showing again the 1 UDP flow sending at 10 megabits per second, and the 31 TCP flow sharing a 10 megabits per second link. And the plot at the left, I'm showing the average throughput over 10 seconds again in the case of the stateless solution. The name and what is doing this is not very important now. And at the right, I'm representing what happens when a stateful solution is employed. So this stateful solution is more complex in the sense that it maintains state for each flow and treats each packet on a per flow basis. So as you can see here, the stateless solution, it's again not very effective in containing the UDP flow. This still gets more than 8 megabits per second, while the TCP flows get very little. In contrast, the stateful solution is successful in containing the UDP flow and protecting the TCP flows. In particular, here, each flow gets more or less its fair rate. In this case, the fair rate is computed as a link capacity, which is 10 megabits per second, over the total number of flows, which is 32. So this gives us a little bit more than 0.3 megabits per second. So notice here the difference in the units on the y-axis of the two plots. However, again, while the stateful solution can provide a much better service, in the same case, in general, they are much more complex to implement. And to illustrate this complexity, consider the example of providing guaranteed services in a stateful solution. So when I'm saying guaranteed services, what I want is to have a service which has the ability to provide per flow bandwidth and delay guarantees. So for example, I want to have the ability to say that a flow will get at least 1 megabit per second, and the end-to-end packet delays are no larger than 100 milliseconds. When you have such a service, first you need to do the admission control. Basically, this means you want to allocate resources from the sender to the receiver on the entire path to make sure that you get the service. And this assume that this is done by the receiver sending a reservation request towards the sender. When a node receives a reservation request, it first decides whether to accept or not this reservation request based on the resources it has, and in terms of bandwidth and link capacity. If it has enough resources, it may decide to accept the reservation. When it accepts the reservation, it also installs some state about that reservation. For example, saying that for this reservation, I have allocated 1 megabit per second on the output link. Then it forwards this reservation request to the next nodes, to the following nodes. If all the nodes along the path accept the reservation is granted, and the sender can start sending data packets. The main point I want to make here is that the difficult problem is not to install this state. The difficult problem is to maintain this state consistent, as it is well known that in a distributed system, in the presence of router and link failures, maintaining the consistency of the state is a very difficult problem. Now, when the sender starts sending data packets, when these packets arrive at a node, the packets are first classified to the flow to which they belong, right? And then they are enqueued in the flows queue. And then they are scheduled based on some parameter which is associated with that flow, like the deadline, right? In this way, these models makes possible to provide for each flow different quality of service, right? So at the limit, a stateful solution will require that every router to perform on the data path per flow classification, per flow buffer management, so this means to enqueue the packet, and when the buffer overflows, to decide what to do with the packet, and the per flow scheduling. And on the control path, it needs to install and maintain per flow state for both the data and the control path. As you can infer from this slide, the data path refers to all the operations which are performed on the packet as the packets travel towards their destination, while the control path refers to all the operations which are dealing to installing and maintaining the state which is required both by the data path in forwarding the packets and the control path in doing the admission control, which I showed you in the previous slide. So to summarize, while the stateless solution are more scalable and robust, the stateful solution can provide more powerful and flexible services. So the natural question is then, can we achieve the best of the two worlds? That is, can we provide network services which are as powerful and as flexible as the one implemented by stateful solutions, while maintaining the scalability and the robustness of the stateless solutions? Well, it turns out that at least in some interesting cases, the answer is yes. Over the past 3 years, we have developed 3 important applications. And these are providing guaranteed services, network support for congestion control, and service differentiation. Now, next I'm going to present you the solution which helps us to address the previous question. At the architectural level, the basic building block of our solution is called a scalable core or SCORE. A SCORE is a trusted and contiguous region of network in which only edge nodes perform per flow management. Core nodes do not perform any per flow management. Since in practice, we expect that in general, these edge nodes to run at a much lower speed than the core nodes, this architecture is highly scalable. Now recall that our main goal is to provide a better service, right, in the internet. In achieving this goal, we propose an approach which consists of 2 steps. So when I want to provide a service, in the first step, we define a reference stateful network that implements the desired service. So recall that these stateful networks are very powerful, and basically, virtually, they can implement any service. Then, in the second step, we try to emulate the functionality of the reference network in a SCORE network. So basically, here we try to provide the same service as the one provided by the stateful network in a more scalable network architecture that is in a score network. To achieve this goal, the main idea is the following. Instead of having these core routers in the stateful solutions, maintaining and managing per flow state, we have the packets carry this state. And the main observation here is that although these core routers do not maintain any per flow state, they can still process packets on a per flow basis because they can process packets based on the state in the packets header. To implement this idea, we propose a technique which is called dynamic packet state. With dynamic packet state, when a packet arrives at the ingress, which recall maintain per flow state, instead some of the state in the packet header. Then the core router processes a packet based on the state in the packet header and based on some internal state. Finally, the egress node removes the state in the packet header. By doing so, note that whatever happens inside of a score domain is transparent to the outside world. To quickly illustrate the capability of this solution, consider again the previous example. And here, I'm showing besides the stateless solution and the stateful solution, also the average throughput over 10 seconds in the case of our solution to provide support for congestion control, which is called core stateless fairy queuing. So as you can see from this graph, at least in this case, we can provide the best of the two worlds. In particular, while the complexity of the core routers in our solution is similar with the complexity, the same basically as the complexity of the routers in the stateless solution, we can provide the same service as in the stateful solution, basically. In particular, each flow gets more or less its fair rate. Next, I'm going to demonstrate step by step how this solution works by taking another example. And this example is providing guaranteed services. Why I'm taking this example? Well, the main reason I'm taking this example here is to demonstrate to you the power and the flexibility of our solution, since the guaranteed service is arguably the stronger semantic service proposed in the context of the stateful networks. However, I want to emphasize that besides the guaranteed services, we have also other applications, like providing fine-grained service differentiation and support for congestion control. I have already shown you some examples for this case. So, the bottom lines, the main point I want to make here is that the guaranteed services, so what you are going to hear next, is just an example, just a point in the space of the services, okay? It's just an instance of the solution. So again, the goal in providing guaranteed services is to provide per flow, delay, and bandwidth guarantees. To achieve this, our approach is to emulate an ideal model in which each flow traverses dedicated links of capacity R. This model is very simple, and R here is a flow reservation. You can easily see that in this model, then the per hop packet service time, so the time it takes to transmit a packet, is simply the packet length over the flow reservation, or this link capacity, R. So in this model, every flow is completely isolated from the other one. And every flow behaves as is the only one who uses a dedicated path of capacity R, where R is a flow reservation. Okay? Now, it's quite easy to see that in this model, if you know the arrival traffic of a flow, if you know the number of hops, then at least theoretically you can meet any end-to-end delay requirements by choosing the appropriate reservation. Okay? The higher the reservation is, the smaller the end-to-end delay will be. So this is exactly the reason for which this model can be used to provide both delay and bandwidth guarantees. Now, as I said, when we want to provide a service, we first start, we have the approach consists of the two steps. So first, we define a reference network which implements this service. In particular, in this case, we provide a reference network in which every router performs on the data path, on the control path per flow admission control, and on the data path, try to enforce this ideal model I was presenting in the previous slide by using a scheduling algorithm called jitter virtual clock. Then, in the second step, we use the dynamic packet state to emulate the functionality of the reference network in the score network. In particular, we do this here by emulating the per flow admission control on the control path, and we emulate these algorithms I told you is jitter virtual clock by using a new algorithm called jitter virtual clock. I'm going to talk about this in a couple of slides, so don't worry about these names. So at this point, I want just to say that providing this per flow delay and service guarantees, so all the previous solution requires that all routers to maintain per flow state. So to the best of my knowledge, what I'm going to present you next is the first solution which can achieve this service in an architecture which is mostly stateless. Next, I'm going to show you how we achieve this. That is, how we eliminate per flow state on the data path, how we eliminate the per flow state on the control path, and then I'm going to end up this section with implementation details and experimental results. On the data path, first, I'm going to talk a little bit more about the ideal model to give you some intuition how it's about his behavior. Then I'm going to present the stateful solution, which tries to approximate the ideal model, and then our stateless solution, which tries to approximate the jitter virtual clock. So first, to provide you more intuition behind how the ideal model is working, consider the following simple example in which a flow traverses 4 nodes. And here, I'm showing to you the arrival of the first 2 packets of the flow at the first node. Okay, so this on the horizontal, I have the time. As I said, in the ideal model, each flow has dedicated links of capacity R, where R is a flow reservation. So what I'm representing here with horizontal lines represent how much it takes to service each packet in the ideal model, and this is, as I said, the packet length over the flow reservation, right? Notice here that I'm assuming that the second packet is smaller than the first one, so it takes less to service it. Now here, I'm showing you the arrival times and the service time in the ideal model of the packet at the second node. What is important to notice here is that the arrival time of a packet is assumed to be no earlier than the time that the last bit of the packet was transmitted by the previous node. And this is because here I am assuming a store and forward router architecture, which is a router architecture in the today's internet. So now here I am showing to you the arrival time and the service time of the 2 packets at the last 2 nodes. And the important things to note here is that because it takes less to service the second packet in the ideal model, the second packet has to wait after the first packet to be processed at the last 2 nodes. The importance of this fact will be hopefully clear in the next slides. Now, as I said, the goal of the stateful solution is to approximate this ideal model. And how is doing that? Well, it's doing that by assuming that each router implements this algorithm, which is called jitter virtual clock. And with jitter virtual clock, each packet is associated an eligible time and deadline. The eligible time is simply the time when the packet starts being serviced in the ideal model. And the deadline is the time when the packets finish being served in the ideal model. Then, jitter virtual clock schedules the eligible packets in the increasing order of their deadlines. And by doing so, it can be shown that jitter virtual clock guarantees that all packets will meet their deadlines. By guaranteeing that all packets meet their deadlines, basically means the jitter virtual clock successfully approximates the ideal model. Okay? Because every packet will not finish being serviced later than the packet will finish in the ideal model. Now, when you want to implement this algorithm, sorry, let me go back a little bit. When you want to implement these algorithms, a question is how you compute this eligible time and the deadlines. In fact, the main question is how you compute the eligible times, because the deadlines can be easily computed by adding to the eligible time the time it takes to service a packet in the ideal model. So next I'm going to go into a little bit more details how to compute these eligible times. So with the first packet, the eligible time is computed either as the arrival time of the packet or as the packet deadline of the previous node. Whichever of these 2 is smaller. The same is true for the second packet as the first 2 nodes. Where things become interesting is at the last 2 nodes. And here, this is because the eligible time of the second packet is computed as the previous packet deadline. Intuitively, this is because, if you remember, in the ideal model, at the last two nodes, the second packet has to wait after the first one to be processed. And why is this important? Well, this is important because by doing this, basically this requires to maintain per-flow state, right? Because when you get a packet, you want to compute its eligible time. But to compute its eligible time, you need to know the deadline of the previous packet. So you need to remember that deadline. You need to maintain the state for that flow, and that state will be at least at that deadline. Our goal is to eliminate this per-flow state. And in this case, this reduces to eliminate the dependence from the previous packet deadline when you compute the eligible time. And to do this, we propose an algorithm which is called coordinated virtual clock. And the main idea here is to make the eligible time greater or equal to the previous packet deadline. So we want to break this dependency between the eligible time and the deadlines of the previous packet. This is the main idea. How we do that? Well, we associate to each packet a slack variable s. And then we delay each eligible time of the packet at each node, excepting the first one, by s. In particular, the eligible time of the packet is computed as the packet deadline of the previous node plus the slack variable s. Notice that also this is true for the first packet, but in the case of the first packet, the slack variable s is 0. Okay? By appropriately choosing the slack variable s and making sure that the eligible time computed in this way is never smaller than the deadline of the previous packet, we eliminate the need to maintain this deadline. Okay? So we eliminate the need to maintain per-flow state. One important observation here is that although the eligible time and the deadlines of the second packet as the intermediate nodes, in the case of our algorithms, are larger than in the case of jitter virtual clock, the eligible time and the deadline of the second packet as the last node are the same in both algorithms. So this basically says that both in our algorithms and in jitter virtual clock, the second, in the worst case, the packet will have the same end-to-end delay bounds. In general, we have proven that if you choose this slack variable s to be the minimum values that guarantees to you that the eligible time of each packet is larger than the deadline, is always larger than the deadline of the previous packet, then both core jitter virtual clock and jitter virtual clock provide the same end-to-end delay bounds. Again, this is an important property because it basically says that we don't lose anything in terms of service by eliminating the per-flow state. Yes?
So at the beginning of the talk, you said that one of the goals was to be resistant to denial of service. What happens if one of your edge routers can maliciously set S to anything it wants and disregard your protocol? Can you still guarantee anything about quality of service?
No. In this case, no. So the assumption here is that I am running everything in a trusted domain. So I trust what the edge nodes are doing. However, I'm going to address that issue in the future work. And I have a slide for that. Another important property here is that the slack variable s can be computed as the ingress, as it depends only on the information which are available as the ingress when the packet arrives. I'm not going to go into details how this is computed. I'll be happy to discuss with you after that. To implement these algorithms, we use dynamic packet state. In particular, each packet will carry in its headers 3 variables. The slack variable s, which is computed and inserted by the ingress node, the flows reset rate, and a new variable which is called a head of schedule. What is important on this slide, and I would like you to take from it, is that the eligible time and the deadlines can be computed only on the information in the packet header and on the information which is available when the packet arrives, arrival time of the packet and the packet length. So we don't need to maintain any per-flow state. So what we did accomplish by doing this? Well, we no longer need to do per-flow classification because we have all the data in the packets. We can compute whatever we want based on the state which is carried by the packet. We don't need to do per-flow buffer management. And in addition, instead of doing per-flow scheduling, we do only per-packet scheduling. And without going into more details, I just want to note here that in this case, doing per-packet scheduling is considerably simpler, has a lower overhead than doing per-flow scheduling. And the reason is because we aggressively shape each flow after each router, we can prove that with a very high probability, the number of packets in the queue is much smaller than the number of flows. Again, I have results here, and I'll be happy to discuss after that. On the control path, we eliminate also the need to maintain the state for the data path, right? When the packet is forwarded, we don't need to maintain a state for that. Now, eliminating per flow state on the data path, it's only half of the solution. The other half is to eliminate the per flow state on the control path. So as I said, whenever you provide a guaranteed service, first, you need to provision the resources on the path, right? You need to make sure that you have enough resources to provide the service. To achieve that, you do what is called admission control, so you want to reserve these resources. And here, I'm going to show you how we achieve this. And we do this by providing a lightweight protocol that obviously does not require core nodes to maintain per flow state. And here, I am assuming that the reservation request is initiated by the ingress, by sending a reservation request message towards the egress. And then each of these nodes, core nodes, decides based on local information only whether to accept or not the reservation. If all the nodes along the path accept the reservation is granted, and the answer is sent back to the ingress. Next, I'm going to show you how one of these core nodes say yes or no. This is the main problem. So here, basically, we care only about bandwidth reservation. So this makes things a little bit easier, in the sense that if you want to allocate only bandwidth, then an easy way to allocate it if you know the available bandwidth on the link, right? If the reservation request is smaller than the available bandwidth, you say yes, otherwise no. And to know this available bandwidth, you need to know this aggregate reservation. So how much you have reserved so far on the output link, right? Now, the problem is that to maintaining this aggregate reservation, so again, how much you have reserved so far, required to maintain some per flow state. Intuitively, this is because the reservation, granting a reservation has a transaction-like semantic. A reservation is granted if and only if all nodes along the path accept the reservation. If the reservation is not granted, the nodes who accepted the reservation have to roll back, have to come to the original, have to go back to the original state. And this is the main reason for which you need to maintain some per flow state. Okay? To address these issues, we propose a solution consisting of 3 steps. In the first step, we estimate an aggregate reservation. The second is we compute an upper bound based on this estimate. And the last one, we use this upper bound for the aggregate reservation instead of the actual reservation for admission control. Notice that by using an upper bound instead of the actual aggregate reservation, we make sure that the resource is never over-provisioned, right? Because basically, when in reality you have, say, 10 megabits per second which are reserved, you may say 11 or 12, right? This will just decrease the available bandwidth. It will make the admission control more conservative. The time limitation is the remaining of the talk. I'm going to only to talk about the first step. Also, this is the most interesting. To estimate this aggregate reservation, in estimating this, we start with a very simple observation. And this is the following. If all flows are sending as their reserve rates, computing this aggregate, it's trivial. You need just to measure this throughput, aggregate throughput. Let me give you an example. So here, you have 2 flows. One with a reservation of 2 megabits per second, and the blue one with a reservation of 3 megabits per second. Now assume that both of these flows send at their reservations. So the first flow sends exactly 2 megabits per second. The second one sends exactly 3 megabits per second. Now, if this node here, the core node, measures the throughput of the 2 flows, it gets more or less 5 megabits per second, which is exactly the aggregate reservation, right? Now, what is the problem with this? The problem is that the flows do not send at the reserve rates, right? What is the solution? The solution is that to associate to each packet a virtual length such that if lengths of all packets of a flow are equal to their virtual length, then the flow sends as its reserve rate. And then you use this virtual length, this is the actual packet's length, to estimate this reservation. Let me be more precise. So virtual length basically is defined as how many bits a flow is entitled to send since the previous packet has departed. And let me take an example. Consider here a flow which has a reservation of 1 megabit per second, and this flow sends 1,000 bit packets. Now, when the first packet departs, because this is the first packet, we just set the virtual length of the packet to the packet length, which is 1,000 in this case. Now, assume the second packet departs after 1.2 milliseconds. Now, during 1.2 milliseconds, the flow is entitled to send 1,200 bits. So we set the virtual length of the second packet to 1,200. Similarly, the virtual length of the third packet, which departs after 1.3 milliseconds, is set to 1,300. And of the fourth packet, which departs after 1.9 milliseconds, to 1,900. Right? So now, if you look here down, you can see clearly that if the lengths of all packets were equal to their virtual lengths instead of the actual lengths, then the flow sends at its desired rate. Yes?
So, Ian, so those virtual lengths are a little more state carried on the packet.
Is that right?
Excuse me? Yes.
So why not just send the reservation rate instead of a virtual length on the packet? Why not send the rate directly?
But then you need to be sure, okay, if you send the reservation, then how do you, because you don't maintain per flow state, how you are going to differentiate between this packet of this packet which carries the reservation and the next packet? You need to make sure that when you count and you add them out, you count one packet once from each flow. This way is basically you go down on the previous idea and just compute the aggregate throughput, assuming the virtual length.
So these are just tokens you're adding up.
Yes, it's like, it's like exactly you compute, it's like computing the throughput, but instead of looking in the field of the packet length, you look in this virtual length field. Yes?
So this is to prevent you from sending packets too early.
To
prevent you from sending packets too early.
So to prevent you to send packets too early, so the function
So
of that.
suppose you didn't do this, then what would end up happening? Would you?
If you don't do that, I have to have another mechanism by which I need to do admission control. So I have to have another mechanism by which I know how much is reserved on the output link so far. I need to know the available bandwidth. Right?
Okay. So
The eligible time is the one which spaces the packet. Okay, because the eligible time is computed as you're using a dedicated link which has a capacity equal to your reservation. Okay, so that will pace, yes.
So these times are measured where?
Okay, so this is as the interest. Okay, so this is a way how your question is about the virtual length or about the.
So it's sort of on this block. That's kind of.
Okay. So let's see. So if we are talking about the virtual length, this is on the clock or the ingress. And we hope, the assumption here is that the skew between the clocks is reasonable.
So you're using the fact that within your score or whatever, you don't have significant clock skew.
Yeah, the only assumption is that the skew between the clocks, it's very small. I don't need the clocks to be synchronized. So to implement this estimation of the aggregate reservation, we use again dynamic packet state. And so in particular, the ingress node when each packet departs, it computes the virtual length for that packet and insert it in the packet header. And then in turn, the core nodes estimate the aggregate reservation on each output link, by assuming that it's like the real length of the packet. So there are several important observations with respect and properties of aggregate reservation estimation algorithm. So the first one is that the estimation algorithm is robust in the presence of control message loss and application. And this is trivially because when we estimate, we use only the information during the current estimation interval. Whatever happens in the previous estimation interval, it's lost, it's forgotten. The second property, in order to compute this estimate, we need to make sure that we receive some packets from each flow. If we don't receive a packet, no packet from a flow, we don't know that flow exists. We don't count for that. So in order to do that, if the flow doesn't send any packet during some time interval, we generate dummy packets. So ingress generates dummy packets. Now, in order to reduce this overhead, one thing you can do is to aggregate all the reservations from one ingress to the egress. And then you send a dummy packet only if no packet departs from the ingress to that egress during this time interval. Yes?
Actually, how long is the estimation of the turn?
How long is it? So this depends. Maybe this will give you a better answer. It's a trade-off, as you can imagine.
Yeah, because the choice will very much affect, like
Yes.
if you have a bursty traffic, or if you have a constant bitrate traffic, or if you have other kind of traffic.
Right. So yeah. So basically, the last property here says that you cannot use the entire link capacity for guaranteed traffic. And this shouldn't come as a surprise because I said we use an upper bound for the aggregate reservation instead of the actual reservation. So you lose. However, if you can play with these constants, you can be, you can use as more as say 80% of the link for this traffic, and then the rest can be easily used by the best effort traffic. So I don't think that this is a serious problem. So by doing this, we also eliminate the need to maintain the state on the control path. So now we know we don't need to maintain any state, any per flow state as a node. The state you see there, this is basically the aggregate reservation on the output link. And the main, I want to emphasize again, is that by doing this, we eliminate the need to maintain the state consistent, the per flow state consistent, which is arguably one of the most difficult problems when designing these stateful algorithms, the stateful algorithms. Let me next go and give you some implementation details and experimental results. So in all these algorithms, you saw that I require that the package to carry some state. So the key question is, where do you insert this state? Well, there are at least three possibilities. The first is to insert it between the link layer and the network layer header, and if you are familiar, this is similar with multi-protocol label switching. The second one is to insert as an IP options, and here we have already reserved an IP option for dynamic packet state. The last one is to find room in the IP header, and while this is not the most elegant solution for performance and convenience issues, we use this last alternative. Basically, to make the long story short, we use 17 bits, 4 bits in the differentiated service field, which are reserved for future use and local use, and 13 bits we reuse by reusing the fragment offset. So probably some of you are familiar with this stealing the bits from the packet header. So basically, we use 17 bits to encode all of these variables. The current implementation it's in FreeBSD and is deployed in a small testbed at CMU consisting of 4 routers and 16 hosts. In addition, we have fully implemented the control and the data paths as I presented in this talk. In addition, we also provide a management and monitoring infrastructure. And here I just want to spend 1 minute on the monitoring infrastructure. So basically, whenever you provide a network service, especially a real-time service, the question is, how do you know that this service is working? And more importantly, if it doesn't work, how do you know why not? And the solution here will be to provide a very fine-grained monitoring infrastructure. But the challenge then is how you do that without impacting the service itself. We partially address these issues by developing a lightweight mechanism that allows continuous monitoring at the packet level. In particular, at the smallest granularity, we can record each packet's header and the arrival time of each packet, its departure time, or if the packet was dropped, the time when it was dropped. Then we use the raw IP to send this information to a monitoring site. So notice that we minimize the impact of the monitoring mechanism on the router in 2 ways. The first is offload as much as we can of the processing on the monitoring site. The second, by using the raw IP to send the information directly from the kernel, we avoid any context switching between the kernel and user space to send out this information. To just give you an illustration of how the entire package is working, consider the following simple example in which you have 3 flows which share a 10 megabits per second link. So this link is between 2 nodes, 2 routers in our testbed. The first flow has a reservation of 1 megabit per second, and this flow sends at 1 megabit per second. The second flow has a reservation of 3 megabits per second, and this flow is on-off. In particular, for 10 seconds, it sends at 3 megabits per second. For the next 10 seconds, it doesn't send anything. The last flow is a best effort, doesn't have any reservation, and sends a little more than 8 megabits per second. So you can see that when all flows are active, you have an offer load of 12 megabits per second, which is larger than the link capacity. Next, I'm going to show you what you can see on this monitor or the monitoring machine in this example. So this is an actual screenshot of our Java interface for our monitoring tool. And the time limitations, I'm going on only to talk about the bottom two plots. The plot at the left represents the arrival rate of each flow before the bottleneck link. The one at the right represents the bandwidth, the bandwidth of each flow after the bottleneck link. So the important things to note here is that the first 2 flows get the reservation. For example, the first flow always gets 1 megabit per second, and the second flow gets 3 megabits per second whenever it sends us 3 megabits per second. In contrast, the third flow gets its bandwidth, its service, only when the second flow doesn't send anything. When the second flow sends, the third flow gets only the remaining bandwidth. Now, due to time limitation, I'm going to skip this slide, which basically illustrates how the aggregate reservation is computed, and go to conclusion and some future work. So in this talk, I have presented to you a network architecture which is scalable core and a technique called dynamic packet state that bridges this long-standing gap between the stateless and stateful solutions. To achieve this, in this work, we developed 2 key ideas. The first is that instead of these core routers to maintain per flow state, we have the packets carry this state. The second is that we use this state to coordinate the action between the edge and core routers in order to emulate the functionality of the stateful network in a more scalable network architecture that is in a core network. Now, arguably, the main contribution of this work is to demonstrate that it's possible to provide these fine-grained, powerful services in a network which is highly scalable. In particular, by using this network architecture and these techniques, we have developed the first scalable solution to provide service guarantees, network support for congestion control, and fine-grained service differentiation. One last point I want to make is this dynamic packet state is compatible with the currently proposed differentiated service architecture. So in particular, I believe that by adding dynamic packet state to diffserve will greatly enhance the functionality of diffserve while requiring minimal changes. Let me spend just 2 or 3 minutes on the future work. So fundamentally, I plan to continue to design this network solution which provides more powerful services, solutions which are highly scalable, robust, incrementally deployable, and easy to manage. And so far, I just touch these 2 issues. And even here is more work to do. So to illustrate this, just let me give you an idea of some future areas which can help to improve the scalability and robustness. So while a core network is a highly scalable architecture, it's by no means the end of the story. In particular, there are 2 potential problems. One is the scalability. So you see, if you remember, I said that a score domain is a trusted and contiguous domain. This basically means that in practice, this will map very well on an ISP, Internet Service Provider domain. But the ISPs are linked to each other, are connected by high-speed routers. in our architecture, this router, it's an edge router. It needs to maintain per flow state. So at the level of the entire overall architecture, this is a weak spot because it hampers the scalability. The next problem is robustness. These core routers process packets, and this is back to your question, process packets based on the state in the packet header. So a natural question, is what happens if a router is misbehaving, is malicious or faulty, and corrupts the state in the packet header, right? Well, it can be shown that in the worst case, this can compromise the service in the network. A possible solution I am investigating now is what I call stateless verifiable architectures. And the idea here is to push the entire complexity at the access points, or if you want, all the way, you can push all the way to the end host. And then you have routers statistically verify the flows. And the hope is here is that by verifying only a small number of flows, you can detect the potential router malfunctions. And for example, now, when these routers detect that a flow misbehaves, it will assume that the upstream router, or maybe the end host, is misbehaving. And then it will try to take measure to protect the downstream traffic against this misbehavior. The main point I want to make here is that designing this architecture is not easy. And the main problem is that whenever you want to say that a router is a flow is misbehaving or not, the decision should be made only using local information, ideally. Because if you in this decision you use external information, the question is how do you trust this information? And one of the possible solutions, not the only one, is to use dynamic packet state for flow verification. And intuitively, this is because, if you remember, the state carried by the packet is a per flow state. Therefore, if a routers monitor a flow, can reconstruct the state of the flow and check the state against the state carried by the packets. So for example, you score it every virtual clock. You can monitor a flow. You can maintain state for that flow. You can use a state to compute the eligible time and the deadline of each packet. And then compare this eligible time and the deadlines with the one which are computed based on only on the information in the packet header. Or a much simpler example is, I can look at a flow and see whether it doesn't send more traffic than it has reserved. And one last slide. Another direction another limitation of the current architecture is not that incrementally deployable. Basically, you need to change one domain at a time. So a natural question here is what services can you provide if you control, only a subset of nodes, right? And one direction I am investigating now is what level of assurance can be provided if you control, for example, only the edge nodes, but not the core nodes. So this is the end of my talk. Thank you very much. Waiting for questions.
Thank you.